All right, so let's say that I've got this situation here where I have train car A and I have train car B. And train car A is moving pretty quickly in this direction, and train car B is just sitting here at rest. It has zero velocity. So at the very beginning, A has some momentum and B has no momentum. Then car A collides with car B. They hit, and after they collide, now car A has no velocity or no momentum. It's not moving. And car B is the one that has all the velocity and is moving this way. And we saw last week that in a situation like this, that the momentum is conserved within a system. And what that means is if we define the system as both car A and car B, if we say that this is the system that we are looking at, we would say that the momentum within that system stays the same. Even though there are changes happening within it, the total amount of momentum is the same. So in other words, we said that if we wanted to look at all the momentum that is in this system in the beginning, if we were trying to determine what is the amount of momentum that is in this system, what we would have to do is we take the momentum of A and we'd have to add it with the momentum of B. Well, at the beginning of this one, all the momentum in the system is within this object here because this guy isn't moving. So all the momentum, we could say, right, we would say the mass and volume of A plus the mass and velocity, the mass and velocity of A and the mass and velocity of B, those added together is the total momentum of that entire system. Well, at the beginning of this one, the mass and velocity of B is nothing because it has zero velocity, and so that goes away. So all the momentum at the beginning is with train car A. And then what we see is they collide, and we're going to assume that after that collision, A basically transfers all of that energy, transfers all of its momentum to B, and now B is the one that is moving this way. And so what we could say is that the mass, or if we were to figure out what is the total momentum of the system, what is the total momentum of the system now at the end, well, we would do the same thing. We would take the mass and velocity of A and we would add it up with the mass and velocity of B to figure out what is the total amount of momentum in this system. Well, A this time isn't moving, and so this would just be 0. And so all the momentum is in B. And so what we could say is that the mass and velocity at the beginning for A is the same as the mass and velocity for B at the end. And that's how we could set up our equation. The mass and velocity at the beginning of A is going to be equal to the mass and velocity of B because momentum is going to be conserved within that system. Now, what if, though, instead, what if we were to say our system is not both cars A and B? What if I said that the system was instead just car B? What if I were to say that's my system that I'm looking at, is just car B and I'm not including car A in that scenario? If I were to do that now my momentum is not conserved, right? Because my system is only car B. And if I were to look at that, at the beginning, what's the amount of momentum that I have in my system? It's nothing because my system is car B and car B is not moving, and so my momentum is 0. Whereas before, if I had my system as car A and car B, well, I had momentum in the system. It was all in car A. And so in this regards, if I were to make car B the system that I was looking at, it would have no momentum at the beginning, and at the end, it would have some momentum. So some external force is acting on the system in that case. And so what the point of all this is to say is that it really matters how we define the system. If I define the system as just car B, then there are some external forces, which would be car A in this case, some external force is going to add momentum to the system. Whereas before, if it was just these two cars together, there's no external forces. All the forces are internal. They're happening within the system, and so momentum stays the same throughout the whole scenario. But if it's just this for the system, then momentum doesn't stay the same throughout the scenario because there's going to be energy added to the system from car A. So it really matters in how we define what the system is. And there's just a couple things we want to define here. The first one is internal forces. So if we have a closed system, and nothing comes in and nothing goes out, we're talking about internal forces, the forces between objects within the system. So this would be, if this, we're talking about this scenario here, where I define the system as both car A and car B, that would be, that we would say that A is an internal force on B because it's within the system, right? That's happening within the system. It's not coming from outside the system. But if I were just to define the system as only car B or only car A, we could do that as well. But if it was only car B, now car A becomes an external force acting on B, because an external force would be a force that's exerted by an object from outside the system, okay? And so, again, we want to be clear on those two things, on when we're dealing with external forces and when we're dealing with internal forces. So basically, whether we're dealing with a closed system or an open system. All right, so let's take a look at this example here. Let's say that I've got two people on skateboards, okay? Once again, we're going to name it person A and person B. It seems like in physics, that's all we ever name things, is thing A and thing B. But we've got person A, we've got person B, and person A is going to give person B a shove, okay? So here he is. He's like, boom, I'm pushing you. And this person's like, yeah, I'm being pushed this way. And so remember, according to Newton's third law, this person is feeling a force this way, in this direction. And because of Newton's third law, this person, even though this guy is not pushing back, this guy A, is still going to feel a force in this direction. And it's going to be equal to this one, just opposite in direction, okay? And because of those forces, we get this guy has a velocity this way and this guy has a velocity this way. So now let's think about this for a second. Let's say we define this system as both A and B. That's our system. Well, let's think about this. At the beginning, they're both just standing there at rest, which means they both have no momentum, right? So in other words, we can say that the mass and velocity of A at the beginning plus the mass and velocity of B at the beginning, so that's the momentum of the system, and we're going to say is equal to the mass and velocity at the end. So the mass and velocity of A at the end and the mass and velocity of B at the end. But now here's the thing. At the beginning, my velocity for A and for B is 0. So there is no momentum in the system. The momentum in the system is nothing, because mass, it would be mass times 0, which is 0 is nothing, and mass times 0, nothing. So my momentum at the beginning is 0, is nothing. But that doesn't make any sense, because at the end, these two guys are moving. They both have momentum, right? But here's the thing. Since they're both moving in opposite directions, so what we're going to do here is, so we got 0 is equal to the mass and velocity of A plus the mass and velocity of B at the end. What we're going to do is we're going to bring one of these terms to the other side here. So we're going to subtract one of these. So let's subtract this So we've got negative mass and velocity of B is equal to mass and velocity of A. And now this actually kind of makes sense, doesn't it? Because if both of these guys have, we set up here, they have the same, they're feeling the same amount of force in each direction, they're both going to have the same amount of momentum, just in different directions, basically. So guy A here has some momentum this way, okay, and guy B here has some momentum this way. They're both the same magnitude but different directions, and so yeah, it actually still within this system, the total momentum is still zero, because negative momentum here will cancel out the positive momentum of this guy. The positive momentum here will cancel out the negative momentum here, and so yeah, actually the total momentum still is, even though they're both moving, the total momentum of the system is actually still zero, just like it was at the beginning, even though they're both moving, which is kind of weird to wrap your brain around. But now let's think about it like this. If I were to say system is just guy B here, now we can see how at the beginning he's got zero momentum, not moving, but in the end he definitely has a momentum that's going in this direction because of this external force, because now guy A is an external force instead of an internal force. And so if we look at that, we would definitely have a momentum in the end. So let's try it. Let's look at an example problem that's similar to this. So we've got an astronaut who's just floating in space, and he has a mass of 84 kilograms. And he fires a thruster, so like a jetpack or something, and that jetpack expels 35 grams of hot gas, and the gas is moving at this velocity when it comes out of the thruster. What is the velocity of the astronaut after firing that shot? So here we've got our astronaut here just chilling in space, and let's see, we're gonna have to make here's a jetpack. He's got the jetpack here, and actually we're gonna have to give him a helmet. Here's his space helmet so he can breathe. And here's the jetpack, and it's gonna force out some air this way. And they tell us, let's see, what do they give us here? We've got the mass of the astronaut, which is 84 kilograms. We've got the initial velocity of the astronaut. So at the very beginning, when he's just at rest, just sitting there before he fires the rocket thrusters here, so 0 meters per second. And as far as the gas goes, okay, because we're looking at the gas and we're looking at the astronaut. So the mass of the gas is 35 grams. We're going to convert that to kilograms right off the bat, so 0.035 kilograms. And the initial velocity would also be 0, because they're both going to be at rest at the beginning, so 0 meters per second. Okay? And then we know that the gas is going to be, in the end, the final velocity of the gas. Whoops, I should put G, not A there. Final velocity of the gas is 875 meters per second. And they want to know, what is the velocity after this? So here's the velocity of the gas. What is the velocity going to be, the new velocity of the astronaut going to be after this? So again, kind of like this example up here, where one thing is going to push on the other thing, and we can either think about it as an external force or an internal force, and then we can try and solve it from there. So let's see, we know that the momentum at the beginning is going to be equal to the momentum in the end if we make this a closed system, okay? So if we make this, the gas and the person, a closed system, okay, we know that the mass and velocity of the astronaut plus the mass and velocity of the gas is going to be equal to the new mass and velocity of the astronaut plus the new mass and velocity of the gas. Now we know that at the beginning though, everything is at rest. So this whole thing right here at the beginning is 0, like this. Whoops. And so what we're going to do is we're going to set these two things equal to each other, but one of them is going to be negative. So I'm going to bring this to the other side. So it's going to be negative mv prime of the astronaut is equal to the positive mv prime of the gas. And so now I have enough to solve for this because I know the mass and velocity of the astronaut, or sorry, the mass and velocity of the gas at the end. I don't know the velocity of the astronaut in the end. So what I'm going to do is I'm going to solve for this term here. So I'm going to divide by negative m over here, divide by negative m here. So velocity of the astronaut is negative. There's my equation. So now I can plug in the numbers. We've got the mass of the gas was 0.035 kilograms times the velocity, which is 875 meters per second, divided by the mass. I should put the mass of the astronaut right here, which is 84 kilograms. Let's see, I gotta find a calculator here and crunch the numbers. So 0.035 times 875 divided by 84. And we should get a final velocity of the astronaut would be 0.36 meters per second.